My name is Daniel Ferenczi. I'm a PhD student, and together with Gergely, Ruda, and Melinda, Tóth, we have been working on an evaluation of using AtomVM for adding fault tolerance to ESP32-based systems. So we have started this research as we were interested in how some aspects of developing and operating IoT systems could be improved. IoT systems have some distinguishing traits. They are distributed by definition. They use multiple devices that have different roles across networking tiers. They should also be scalable. We should be able to add and remove devices, especially sensors that might be deployed on the field as effortlessly as possible. Also, as the system, perhaps even the applications are distributed and heterogeneous, testing can be difficult. The whole system might be based on different technologies across the networking tiers. And finally, devices might use different types of hardware, ranging from microcontrollers to servers. Many of these characteristics we found to be in line with Erlang's highlighted features, like fault tolerance and language level support for building distributed systems. If practically would make many of the aspects of IoT development easier, ranging from the design of a distributed application to simplifying the software stack used in the complete system. But supporting the variety of hardware that can be present in a complete system still requires some additional work, however, as hardware in these setups can range from powerful servers with gigabytes of memory and multi-core processors on the higher levels of a setup to simple microcontrollers with only a few kilobytes of memory on the field level. They also differ in how much power they require to operate. Some use cases may require field-level devices to work on battery power exclusively. Using Erlang in IoT is now supported in 3 projects: NERS, GRISP, and AtomVM. NERS targets devices in the range of Raspberry Pis or BeagleBones that typically run on continuous power and may have hundreds of megabytes of memory. NERS provides a specialized distribution of Beam on a stripped-down operating system that is specialized for these devices. GRISP, on the other hand, runs on specialized hardware and brings Beam as close to the hardware as possible to allow a tight integration between the runtime and the device's real-time operating system, and this allows hard real-time event handling. AtomVM is very different in this regard, as it is a reimplementation of Beam, targeting very low-powered microcontrollers with memory in the range of a few hundred kilobytes, and these may even run on battery. We are particularly interested in what we can achieve with embedded devices with memory in the range of a few hundred kilobytes. Therefore, we chose to look at AtomVM in more detail. AtomVM is still a work in progress, and while it lacks features of complete Beam, it still allows typical features like running hundreds of concurrent processes in those few hundred kilobytes of memory your device may have. It allows monitoring them. You can construct OTP behaviors, and it provides an Erlang interface for working with the hardware's features. Supervision trees, lightweight processing help build fault-tolerant applications for single devices. Multiple microcontroller families are supported, but we did our experiments on the ESP32 development boards. So ESP32 is a family of microcontrollers. which made this choice as AtomVM has the highest level of support for this board. This includes general purpose I/O, which is practical for interfacing with any sensors that we might put on the board. This includes universal asynchronous receiver transmitter. This made sending and receiving data to the board through a serial communication easier. This is useful for our experiments. And a networking stack lets us experiment with applications and hardware sending data. And in total, these interfaces help us send data, read outputs easily. Finally, we also have LoRa. That is a long-range communication technology that is popular in IoT systems. This helps us experiment in scenarios where we are using a communication technique between devices that could be used in some real-world use cases. Altogether, these features help us tailor experiments similar to what can be seen in the real world. So we chose the S3 version of ESP32. This hardware in particular includes 512 kilobytes of memory, a dual-core processor, connectivity options through Wi-Fi, Bluetooth, and LoRa. It can also be put to deep sleep. This is a state in which a device barely consumes any power. Using deep sleep when the device has no task to perform allows reducing the device's power consumption and prolong the time it can run from battery. And finally, the devices are also supported by the Arduino IDE. This allows us building C++ applications for them easily so that we can compare the performance of an AtomVM Erlang application to that of a traditional implementation quite easily. So apart from the features AtomVM we already highlighted from AtomVM, some recent development releases also include partial support for the distributed Erlang protocol. This lets us send and receive Erlang messages in a language-native way between devices, even with computers running real beam. Doing process monitoring between the devices is also supported, but we do have limited connectivity options as not all features of distributed Erlang are implemented yet. Our goal was to add fault tolerance to an ESP32-based system using all these features we have highlighted from AtomVM. In a typical IoT setup, we have some powerful server nodes on the top tiers. Gateway nodes are connected to these servers, and they receive data from a potentially large number of sensor nodes, typically through some sort of wireless communication method. We wanted to add fault tolerance to the gateway nodes in such a system. We found them interesting as the failure of such a component can lead to data loss in the complete system. So let us start by looking at a non-fault tolerant system to which we later add fault tolerance. We start with what we refer to as a gateway. This is a LoRa server, and it has the purpose of receiving LoRa frames from field devices. These client devices are sending data wirelessly through LoRa continuously to our server. Finally, our server is connected to a PC to which it can forward the data it gathers. It also lets us collect the server's memory metrics so that we can see consumption, any bottlenecks, any adverse effects that we provoke with our configurations. And we can change the configuration as well on LoRa server according to the experiments we are performing. The LoRa server here is a point of failure, as in the case of an error, we can't gather data from the clients anymore. So to add fault tolerance, we should start by adding a second LoRa server. But now we have the challenge of only running the LoRa receiver process on one of the servers to avoid any sort of data duplication. And we solve this at the moment by running a Beam node on our PC. This node manages LoRa receiver processes on these LoRa servers. It keeps track of servers in the system and ensures that a single receiver process is operating at a given time. The management node checks server processes using process monitors through distributed Erlang, and the messages that trigger the activate and sends messages that trigger the activation of LoRa receivers also through distributed Erlang. To summarize, our system has 4 types of components. Client nodes send data periodically through LoRa to a server node. The server node capable of receiving data is selected by the management node. The memory consumption and overall performance of the server nodes is followed from a developer PC. Client and server nodes run AtomVM on an ESP32 hardware, while the management node runs Beam on a PC. The management node and the servers communicate through distributed Erlang. We do fault tolerance by a logic that detects failure of the LoRa receiving process and activates it on an idle server. As our fault tolerance implementation is based on distributed Erlang, our main goal was to test how robustly distributed Erlang works on these devices. The server nodes receive LoRa frames every 300 milliseconds or 500 milliseconds continuously, depending on our configuration, as this is their main role. We chose these rates for receiving messages, as a single server node acting as a gateway might receive messages frequently if there is a large amount of clients sending messages in the deployment. We check how running additional processes causes instability for LoRa frame reception and whether any instability can be detected from the process monitors on the management node. We tried 2 types of loads with additional processes, reading voltage values on a given pin of the device. We chose this to be analogous to interacting with additional sensor components that could be added to the real device. We also experimented with adding computationally more demanding tasks, like verifying whether numbers of different sizes are prime. In a base case, where the server only receives LoRa frames without doing any additional work, we tested fault tolerance by simply powering off the active server. Absence was detected by the process monitor on the management node in a few seconds, and the management node started LoRa reception on one of the idle servers. In total, a backup node took over LoRa reception in about 5 seconds. Adding any sort of additional work, however, slowed down processing LoRa messages. This could be noticed particularly well on the 300 millisecond configuration, and where data here was not lost by default when we were not running any additional work. Even adding a single additional process resulted in the node losing data. On the 500 millisecond configuration, we needed to add about 4 processes to make data processing unreliable. And by unreliable, we mean that our server nodes started losing data, and we found that they became so overloaded that if they were not added to a distributed Erlang configuration from the start, they were not, we could not add them while they were overloaded. If they were added beforehand, however, we found that the receiver processes appear healthy from monitors on the management node, even though for all particular processes the node was absolutely unreliable. As a summary, AtomVM requires about 250 kilobytes of memory, while starting distributed Erlang increases this to 32 kilobytes. A heavy load on a system like processing wireless messages that arrive frequently causes the node to become unresponsive, unstable in practice. These problems might not surface through monitoring. We kept adding new processes to an already unstable system to find a point at which the monitor detects any problems with the server node. Eventually, after adding about 200 additional processes, the system became so unresponsive that the watchdog restarted the complete system, and finally the management node detected that the monitoring process was missing and restarted it on one of the idle boards. We concluded that aligning the watchdog with the workload that is to be expected on the device is still required if we want cross-node process monitoring to react on practical node responsiveness. Altogether, we were only able to start additional processes when receiving data at the rate of 500 milliseconds. But even in this scenario, we were only able to start 3 lightweight processes that checked a voltage or verified a 4-digit, or verified whether a 4-digit number is prime. This work is part of our ongoing research in finding industrial applications of Erlang, especially in the domain of precision agriculture and industrial automation. For this work, we want to explore different device onboarding flows. Ideally, we would want server nodes to connect to a central server autonomously. We were not able to do this in our current experiment because of some limitations on how distributed Erlang was supported on AtomVM. Perhaps we would even want to do in the future process management on the server nodes without the need of a dedicated management node. We are following the development of distributed Erlang features on AtomVM to see how these expand our options. This would also help us run distributed Erlang applications on embedded boards. We also want to experiment with aggregating data on the client or server nodes. Such experiment would fit IoT and would highlight how Erlang helps building concurrent applications that perform different tasks, even on embedded devices. Aggregating data locally, especially on sensor level nodes, will also be a fitting example of using Erlang processes to easily add encapsulated features. Altogether, in our research so far, we measured that 512 kilobytes of memory can host hundreds of lightweight processes. We can use this to build applications in the OTP way with behaviors. With distributed Erlang, we can manage processes between nodes and build fault tolerance around this, although we should account for any expected load on the system. As opposed to using Arduino IDE and C++, we found fast compilation times, dynamic types, and pattern matching very convenient for iterating our software fast. And with that, I would be very happy to answer any questions.
thank you very much. Well, I'm not the chair, but I'm at the front. So I guess if there are any questions, hopefully the audio will come through.